Yeah, I'm quite happy to welcome Mathieu Houryp to this CTA seminar. He's going to tell us about fixed point properties in the category of represented spaces.
Okay, so thank you very much for the invitation, and thank you everyone for coming. So let me try to share. So I guess I should select the desktop. Okay. Then, so is it fine?
We now see your desktop.
Okay. You don't. So you don't see the slides.
No.
Okay. So let's try again. Is it working?
Now we have some slides. Yeah.
Yes. Okay. Good. Okay. So yeah. So I'm going to talk about the fixed point property for represented spaces. So some high-level motivation. So yeah, as you know, many fields in mathematics have their fixed point theorems, very famous ones like in topology, order theory, and so on. Yeah, so in computability theory, there is also the famous recursion theorem due to Kleene, which is the fixed point theorem for computability theory. So which was originally for partial functions and CE sets, but which was extended by Herreshoff to more general sets, so numbered sets, so countable sets for which you have an indexing of the element by natural numbers. And so what about computable analysis? So so there was an extension of Herreshoff theory to represented spaces by Kreitz and Weihar in 85. So it was a long time ago. So I mean, we could imagine that the question is over, and there is a fixed point theorem for computable analysis, and we can use that. So, but we will see that there are this version is in some way not always satisfying. So the main reason is that in number sets, usually the numbering is total. So every natural number is a code for an object, but usually for represented spaces, it's not the case. So the representation is partial, and the way to deal with this partiality makes things not so natural. And so you can invent several versions of fixed point property for represented spaces. And so the one which was proved by Kreitz and Weihar does not satisfy some properties that we would like. Okay, so just to summarize, in computability theory, the fixed point theorem is about number sets and computable multivalued functions. So the natural extension to computable analysis would be for represented spaces and continuous multivalued functions. So there are two ways in which there is a difference between computability theory and computable analysis. So the first one is that for numbered sets, the codes of the objects are discrete, they are natural numbers. And for represented spaces, they are continuous objects. So typically elements of the Baire space. So that's the first difference. And the second difference is that in computable analysis, we are not only interested in computable functions, but also by continuous functions. And here I will just talk about continuous things. And when you work with continuous objects, you can say sometimes a bit more than when looking at computable objects because they behave more smoothly in some way. Okay, so when going from computability theory to computable analysis, from numbered sets to represented spaces, there are a few things that you expect will extend without any problem. So for instance, these results in the theory of numberings. So the first one is due to Herreshoff, which says that a total numbering, a totally numbered set satisfies the second recursion theorem if and only if it's pre-complete. So there is a kind of characterization of which number sets satisfy the fixed point property. And an example of sets which satisfy the fixed point property is given by some domains from domain theory with some effective assumptions. So we have a kind of general result, which is a characterization, and some class of numbered sets satisfy this fixed point theorem. So without any surprise, this kind of results will extend easily to represented spaces. But again, there is some subtlety in the way you phrase and you define fixed point because the representation is usually partial. Okay, but the more interesting part is that when you look at continuous functions rather than computable functions, there are some questions you can answer, and there are some results that become available. And so the most important ones that we will see is that in many cases, you can give a full characterization of which spaces have the fixed point property. And there are a few questions that also we can have an understanding of. So for instance, why is it the case in practice that each time we have a space with the fixed point property, this property holds uniformly? So if you give me a function or a multi-valued function, I can continuously or even sometimes computably, I can compute a fixed point for it in a uniform way. And another question, which is, okay, as you know, the fixed points and the recursion theorem are very related to the diagonal argument. So in the continuous setting, we can ask whether the diagonal argument is the only way to prove the fixed point properties. So we will have some partial answers to these kind of questions. Okay, so just a slide that is probably useless, but anyway, I just briefly recall the basic notions. So the bare space is denoted by this n. A represented space is a pair of a set and a partial surjective function from the bare space to X. So a multi-valued function, I will call it multifunction for short, a multifunction from X to Y. So it sends a point to a set essentially. So it is computable if it has a computable realizer. And what is a computable realizer? It's some algorithm on bare space, which takes a name of a point X and outputs a name of a point in the image of X. And of course, the Y does not only depend on X, but also on the name, the particular name of X that was fed to F. And we say that a multifunction is continuous if it has a continuous realizer. Okay, so now let's go into more details and look at the fixed point property for represented spaces. So we say that a represented space has the fixed point property, if every continuous multifunction from X to X has a fixed point, which is a point which belongs to its image under H. So it's useful to have the intuition of what is a fixed point free function, so a function without fixed point. So it's like an algorithm that takes some point X and outputs another element, some X prime different from X, which may differ, which may depend on the particular name of X that was given. Okay, so just as a warm-up, we can look at a few spaces. So all of these have some natural representation. So the real numbers, does it have the fixed point property? Well, no. There is even a continuous function which has no fixed point. So this one is a single valued function. It's not a multifunction, it's more than that. So what about the interval 0, 1? So again, it does not have the fixed point property, but here we know every continuous function has a fixed point there. However, it's possible to build a fixed point free multi-function. So given a real number in 0, 1, you can quickly test whether it's more on the left or on the right. If it's on the left, you output 1. If it's on the right, you output 0. So it's necessarily multi-valued, but it's a fixed point free. So what about this third space, which is 0, 1, where you represent a real number by a growing sequence of rational number converging to it? So like the space of left C numbers in some way. So yes, this one has the fixed point property. So what about this one where we remove 0? It does not have the fixed point property because this function, x over 2, has no fixed point. The only fixed point is 0, it's outside the space. What about this point? This set, if we remove 1, we can have a similar function without any fixed point. So P omega is the power set of n of the natural numbers with the Scott topology. So you represent a set by enumerating the set in any order. So this space has the fixed point property. So if you enumerate a set, if someone enumerates a set, it's not possible to enumerate a different set in general. So it's like the recursion theorem, but in a continuous way. So what about the space of sigma n subsets of Baire? So it's not hard to see how such a set can be represented. I mean, it's you can do it inductively by over n. For instance, a sigma 2 set, it's a union of pi 1 sets. So you represent by a sequence of closed sets whose union is the set. There is a very natural representation. And this space has the fixed point property, but the space of delta n subsets does not have, because the complement function has no fixed point. Okay. So we would like to understand, okay, what are the special properties of these spaces which imply the fixed point property or the opposite? So here I showed you why some spaces do not have the fixed point property. So why these spaces have the fixed point property? So how is it proved? Well, it's like the recursion theorem in computability theory. It's the diagonal argument. So the first thing to see is that there is a continuous surjection from Baire space to the continuous functions from Baire space to X. So it's like the big matrix in the diagonal argument. So this surjection implies that X has the fixed point property. So it's the usual diagonal argument. I just give it because there is some point I want to discuss. So if you are given some continuous multifunction H like that, then you can find a fixed point for H by taking the diagonal. So you take the diagonal, which is phi of pp, and you apply H on the diagonal. So you get a function f from Baire to X. It's a continuous function, so it should be some phi of p0. And then you can easily check that this phi of p0 is a fixed point of H. So it's the usual argument. But there is just one detail which is important, is that actually, so H is a multi-valued function. So when you look at phi, H of phi of pp, this is a multi-valued function of p. But because p is an element of the Baire space, you know, the Baire space, the elements are their own names. So each element has a unique name. So if you have a multifunction, a continuous multifunction, actually the realizer just outputs always the same element because there is only one name. So if you have a continuous multifunction from the Baire space, it always has a continuous single valued selector. So that's why from H we can build a single valued function f. Okay, so that's a key point which will be important in the end of the talk. Yeah, so we use the diagonal argument to prove the fixed point property. some property associated to the fixed point property. So if you have a represented space, you have a topology, which is the final topology of the representation. So you take the sets whose pre-image under the representation is open in bare space. And there is this classical specialization pre-order over the space. So you say X is smaller than Y if every neighborhood of X contains Y. And an easy result is that if X has the fixed point property, then it must have a least element for this pre-order. And this is not very difficult. So let's show that if X has no least element, it does not have the fixed point property. So having no least element, it's not hard to see that it's equivalent to the following property. There exists an open cover of the space, so a cover by open sets, such that no one of these open sets covers the space alone. Okay, and once you have that, then it's easy to build a fixed point free multifunction. So given a point X, you want to define some X prime different from X. So you are given a point X, you look for some index I such that this point X is in UI. You know it exists, so you can wait, and when you have it, we know UI does not cover the space, so there is some other point, X prime, which is not in UI, and so we output this point. Okay, so because X is in UI and X prime is not, X prime is always different from X. Okay, so this is a simple property that allow you to reject many spaces. So for instance, the space must be compact, because if you have a least element, it must be compact, because when you have an open cover, the least element must be in one of the open sets, but then this open set must cover the whole space, because the neighborhood of the least element is also a neighborhood of every other point. So it's compact, and it cannot be T1 unless X is very trivial. It's just 1 point. So yeah, if it's like that, if there are 2 points which are separated by open sets, they are incomparable. So there is no least element. So you can reject many spaces. So if we go back to the first examples, we see, for instance, that this space where we remove 0, it does not have a least element. That's why it does not have the fixed point property. However, there is this space which has a least element, 0, but does not have the fixed point property. But yeah, but each time you see a yes here, you must see a yes there. Okay, so now let's look at a refinement of the fixed point property, which is the uniform fixed point property. So it's based on the observation that for usual spaces, for instance, these ones, so they satisfy the fixed point property, but they also satisfy a uniform version of it, which means if you give me some h, I can uniformly, and even in a computable way, I can find a fixed point for h. So let's put this into a definition. So it's like in the second recursion theorem, where you can compute the fixed point from the function. So let's put that into a definition. But first, let's remark that there was already a definition for represented spaces given by Kreitz and Weierauch. So it was called the T recursion theorem. So T is for topology. So it's not about computable function, but continuous functions. So there was a kind of uniform fixed point property. However, it does not imply the fixed point property as we have defined it. And the issue is, again, about the domain of the representation. Because the representation is partial, the exact definition is very sensitive on how you manage this partiality. So the idea of the uniform fixed point property is really easy. So a space has the uniform fixed point property if given some realizer of potential multifunction, we can find from it in a continuous way, we can find a fixed point, so which is a name P, such that we have this equality. Okay, so it's a name of a point, which is also such that the image is in, sorry, it's the name of a point which belongs to the image of the point in some way. So this is the idea, but you have to be careful about, yeah, the fact that the representation is partial, the function h is partial. So how do we want to assume more about P? So yeah, it looks frightening at first because there are many possible ways to define this, but it turns out that I wouldn't say the right definition, but particularly useful one is to do this. So we just add the red part here. So we want that we always produce a valid name, so some element of the domain of the representation. And we want that if, oh, sorry, so this is P here, it's not X. If moreover P is in the domain of this, so if H is well defined at P, then it is a fixed point in this way. So this definition is looks a bit ugly at first, but we will see some nice characterizations which make it more usable. And just to compare with the definition of Kreitz and Beihau, so they assume that H is total, so it's only for total functions, and they do not require that P is in the domain of the representation, which means it could be that P is a fixed point in the sense that both sides are not defined. So P is not really a name of a point. So it could be that H has no fixed point, but P is a fixed point in the weaker sense that both sides are undefined. But we really want that it's always defined. It's always in the domain. So, okay, so that's the definition we will work with. And as I said, there is a much nicer characterization. So a represented space has the uniform fixed point property if and only if every partial function has a total extension. Okay, so this is much easier to work with because it's clear what it says, and usually it's easier to prove. So the first reason why this definition is probably good is that there is a nice characterization. The other reason is that the same notion actually pops out in other papers. So there is a recent paper by Vasco and Guido where they introduced the notion of multi-retraceable space. And actually it coincides with this. So they give other characterizations of this property. So it's kind of robust property. And also it's equivalent to a notion introduced by Vasco in another paper, which is that this multifunction, like the maximal fixed point free multifunction, is effectively discontinuous. So this is equivalent to saying that X has the uniform fixed point property. Okay, so it has lots of characterization, and in particular, this equivalence implies an interesting result that if you assume the axiom of determinacy, then the fixed point property is equivalent to the uniform one. Okay, so this result explains why in practice for natural spaces, each time we have the fixed point property, we have actually the uniform one. Let's just look at the idea of the proof to see how it works. So of course it's a game. You have two players. The first one plays x1, the second one plays x2, and the player 2 wins if she manages to produce a different point. So x2, if x2 is different from x1. So a winning strategy for player 2 is a fixed point free continuous multifunction. And it's not very difficult to see that a winning strategy for player one is actually the uniform fixed point property. So with the axiom of determinacy, one of them has a winning strategy. Okay, so of course I'm not claiming that the axiom of determinacy is correct, but this result shows actually that if you have a definable space in some way, you can expect the equivalence to hold. And sometimes you can even prove it without the axiom of determinacy. And we will see many examples of this, where we can drop the axiom of determinacy. And of course, when you can prove something with the axiom of determinacy, usually you can also prove that you really need this axiom. And indeed, using the axiom of choice, we can build a counterexample where these two properties are not equivalent. So just a few words about that. So the space would be the set with two elements. We take some subset of the bare space, and the representation is the characteristic function of A. And then we can build A so that the space has the properties we want. So for instance, the fixed point property can be rephrased by saying that A is not weight reducible to its complement. And so like when constructing a Bernstein set, we can build A so that it does not satisfy the equivalence. Okay. So I'm going too slowly, or there is too much, but okay, I will try to manage that. So yeah, so it would be nice to have an admissibly represented space where the topology and the representation agree in some way that satisfy the fixed point property, but not the uniform version. Another consequence of this is that, so we can say something about this question. Is the diagonal argument the only way to prove the fixed point property? So the diagonal argument is this: if you have a surjection here, then X has the fixed point property. And it turns out that because of the previous results, this is an equivalence assuming the axiom of determinacy. Because this property is sandwiched between FPP and the UFPP, so they become equivalent. So in many cases, yes, this is essentially the only way to prove the fixed point property. Okay, maybe I will skip this because I don't have much time, but just to say that if we have a subset of some space, the fact that the subspace has the fixed point property is related to its descriptive complexity. And the result is that if the set has one of the fixed point properties, then it should not be more complex than equality on the space. So that's, for instance, a way to prove that a space that does not have the fixed point property. But I don't spend much time there. And I will go more directly to this. Okay. So now we are going to look at particular classes of represented spaces and prove characterizations of the fixed point property. And at the same time, we will prove that the fixed point property and the uniform fixed point property are equivalent for these spaces. So the first result is that if we take a topological space, which is countably based, T0, with the standard representation. So a point is represented by enumerating its basic neighborhood. So in that case, the fixed point property is equivalent to the uniform one, and it is equivalent to this fourth condition that X is a continuous DCPO with the Scott topology, and pointed means with the least element. So it was more or less like folklore that if that such domains, such pointed omega continuous DCPOs satisfy the fixed point property, but it's actually equivalent for a countably based space. So, so it's important to note that we do not assume the axiom of determinacy, which at first I was quite surprised by this, because usually to get rid of the axiom of determinacy, you need to assume that your sets are defined or Borel or something. But here X may not be Borel, but yeah, the properties of the ordering makes this equivalence hold. So that there is some additional structure which allow to drop the axiom of determinacy. So let's see a few ideas about how to prove this implication. So the fixed point property implies that the ordering on the space is a DCPO, directed complete partial order, and it's omega continuous. So I don't give the definition, but I will give some hints. So let's take a subset of the power set of n ordered by inclusion, and we will see that if it's not directed complete, we can build a fixed point free multifunction. If it's not omega continuous, we can also build a fixed point free multifunction. So the first point, I will just take an example. So you take the power set of natural numbers and you remove the maximal element, you get x. It's easy to build a function, even a continuous function, which has no fixed point. So you give me a set, you enumerate a set, which is not the full set, and I have to enumerate another set. So what should we do? We can enumerate a finite set up to the point where up to some n, which is not in A. So we are given A. A does not contain everything. So there is an n which is not in A. And so we just enumerate this set. And this set will be different from A. Okay, this is very easy. But what are we really using here? We are really using that X is not directed complete. So these finite sets belong to X, but they don't have a supremum, a great least upper bound in X, which is omega. So yeah, and so more generally, if X is not a DCPO, you can apply the same kind of strategy. So if you're not a DCPO, there is a fixed point free multifunction. And now let's go to the other point about omega continuity. So let's take the space of infinite sets and you add the empty set. So you have an element at the bottom and all the infinite sets above. So again, it's not hard to build a fixed point free multifunction. If you give me A in that X, in that set, I can enumerate another set. So given A, we start producing omega. So we enumerate all the natural numbers one by one. And we also wait to see whether A is non-empty. And if someday we see that A is non-empty, then we know that A is infinite. So we can stop our enumeration. We have enumerated just finitely many elements. So we know A must contain a new element. And so we wait for such a fresh number, and then we output omega minus this element. So we have produced a new set. So what are we using here about X? Well, we are using that it's not omega continuous. So let me explain. So there is this relation that we can define over X. We say that A is topologically way below B if B belongs to the interior of A. Okay, just some definition. And omega continuity means that this relation is rich and that every B is the supremum of the A's which are way below B. And here in this particular X, this relation is not rich. It's very poor, actually. If A is non-empty, then it's not way below omega. So the only element which is way below omega is the empty set. And that's what we are using. If A is non-empty, we can wait. We know that something will happen which make the strategy possible. So I don't explain more detail, but this is really what we are using here. Okay, so it gives some idea about the proof of the result. Just a remark that we are interested in multi-valued functions and not single-valued functions. So for multi-valued functions, we can have characterizations, and we could wonder whether the fixed point property for single-valued functions could be characterized in the same way, but it looks much harder. And let me take an example. For finite spaces, so the previous results show that the fixed point property is equivalent to this. The space has a least element, that's it. It's a very easy characterization. But for the fixed point property for single-valued continuous function is much harder, and actually it's an open problem because it's equivalent to the fixed point property for finite posets and order-preserving functions, and this problem is has no like general solution. So yeah, so multi-functions are much more flexible than single-valued ones, and that's why we can have characterizations. And let me state the other important result is that if we have a represented space X, we can build the space of open subsets of X. And it turns out that we can exactly identify when this space of open sets has the fixed point property. And it's exactly when X is countably based. And again, the uniform fixed point property is equivalent to the fixed point property. And again, a remark about multifunctions. Whatever X is, O of X is a lattice, a complete lattice. And so Tarski theorem implies that continuous functions have always fixed points. But for multifunctions, there is a difference whether X is countably based or not. So again, let me give a brief idea of the proof. So let me show an idea of why, if X is not countably based, we can build a fixed point free multifunction. So there is a big difference between countably based spaces and the others, which is that in a countably based space, like let's say the bare space, when you enumerate an open set, what you do is you actually, at each step, you have enumerated some subset, which is open. So giving an open set is just giving a growing sequence of open sets. But when the space is not countably based, it's not true. The partial sets in the enumeration are not always open. So let me illustrate the idea in a space where this is even worse, where each partial enumeration has empty interior. So it's not open, and actually it contains no non-empty open sets. So it's not always the case, but we can adapt the next strategy in the general case. So let's assume this just for the talk. So we want to build a fixed point free multifunction. So we are given an open set, and we want to produce another one. So we start with we choose some V, and we start enumerating V. So V0, V1, and we wait to see whether U is non-empty. So if at some stage S we see that U is non-empty, we pause. So we stop enumerating V, And we realized that, okay, VS has empty interior, so it cannot contain U. Okay, so this U will eventually, we can pause and wait, and we will see at some point that U escapes from VS. So at some stage, we have this situation. And then we are almost done, because it means like the opponent has enumerated elements that we do not have enumerated so far. And so we can use that and choose some other open set V prime, which does not contain U. And now we will enumerate V prime instead of V. So that's the idea. Okay, I had a third part, but I see that the time is running, so I will just maybe very briefly say something. So actually, originally the motivation for this work was to study the base complexity of topological spaces, because so when you have a countably based space, okay, you have a basis which you can index by the natural numbers. So for other spaces, there is this base complexity classification where you can wonder which Y do I need to index a basis of the space. So it was introduced a few years ago by Mathieu Debrecht, Matthias Schroeder, and Victor Selivanov. And it turns out that the spaces of higher order continuous functions, the Klinik-Reisel spaces, can be used to do the classification. So you start from natural numbers, the bare space, and you iterate the process of taking function spaces like that. So the countably based spaces are the N0 based spaces. So for instance, the open subsets of bare space, this is not countably based, but it is N1, it is bare based, it is N1 based. And the space, the Klinik-Reisel space itself, N alpha, is N alpha plus 1 based, but it was open whether we can improve this. Is it N alpha based? And a related question is the hierarchy of base complexity proper? Does it collapse or not? So, so what I obtain is that indeed this is optimal. So N alpha is N alpha plus 1 based, but no more. And the proof uses really the existence of fixed point free multifunctions and a refinement of the diagonal argument. But I don't have time to say more than that. So I will stop here and I will just go to the last slide with some references which I mentioned during the talk. So thank you very much for your attention.
Thanks for that very nice talk, and for giving the plenty of time for questions now. I will suppress the urge to just jump right in and gives the audience a chance to raise them. And just raise a virtual hand, or if you feel bold, unmute yourself and start talking. Someone else jumping at it. Sort of, how much does it make sense to want the computable versions of these? So sort of on the one hand, rather than just saying the sort of maximum fixed point free multivariate function should be continuous, you could ask for that to be computable, and on the other hand, the uniform fixed point property is also that you would want in a computable version.
Yeah. So some of the results. So yeah, you can define the computable uniform version, and some of the basic results hold without any trouble. But of course, so of course, everything which involves the axiom of determinacy completely breaks. Of course, the characterization of the countably based spaces does not hold. So I don't think I have any counterexample in mind, but it's probably not very hard to show. And the proof is not constructive. You know, it's really, if you are not a DCPO, then you can build something, but you will need a witness that it's not a DCPO, a computable witness for that, and so on. So all this is very non-effective. But yeah, but in practice, of course, for natural spaces, the computable version will work. Yeah, so unless you build your space so that the equivalence fails in a computable way, usually you can expect that everything will be nice.
I had something in mind I really wanted to ask about something in the earlier part, but I'm missing it right now. For your, that was not it, but that was the third question at most. For your argument that for non-countably based spaces, you can construct the fixed point free multivariate function on the open subsets.
Yes.
How intricate is this argument that sort of once your opponent has grown beyond what you currently have, that you can actually get and sort of extend what you have to an open set without catching up?
So what is the question exactly?
I think on the next slide you have this, yeah, you have this diagram here. Now here you are saying, okay, you will at some point grow out of your current approximation V of S, but since V of S is not open, you can't stop there, so you have to add stuff. And
so the question is, how can we do that, or what's behind that? Yeah, so okay, so we know there is a point there which is in U but not in VS, and we are using a special property that VS is upward closed, so or saturated. So each point in so VS is an intersection of open sets. So if you have a point which is in U but not in VS, then the closure of this point, which is the elements below the point, is also disjoint from VS. And so the complement of this closure is an open set, is V prime.
Okay, yeah, thanks.
And we need this special property. That's why we need X to be admissibly represented. If X is not, I didn't think about whether the proof works, but this point does not work.
I mean, then you could of course have annoying things like take an X that doesn't have any non-trivial open sets. Then I mean, don't think there's any meaningful statements there.
Yeah.
Okay. Last chance for anyone else to ask a question. Nothing then. I think we should thank Mathieu once more.
Thank you.